This is part 2 of the opening lectures on the theory of special relativity. We now start to take a look at the consequences of the postulates of special relativity. As you'll see, the consequences are strange. Prior to doing so, however, we have to define the following terms. Okay, first of all, very simply, we have what is referred to as an event. An event is basically something that happens. However, if you were going to describe an event to somebody else, you would basically have to state two things. You have to state when and where the event occurred. So then therefore, very simply, an event is an occurrence in space and time. Okay, and then we're going to have a time interval between two events. There are two types of time intervals. The first is called an improper time interval. An improper time interval is a time interval between two events that occur in different locations. So consider the following scenario involving me snapping my fingers to represent events. Let's consider first of all the room, yourselves, to be a stationary reference frame. And then opposite sides of the room I have two students. I have over here, for example, student A, and then over here, student B. Student A and student B are not moving relative to each other. Therefore, they are in the same reference frame. Now let's say that I'm going to be a moving reference frame. I'm going to be moving through the room at a constant velocity u. So I'm another inertial reference frame. I'm at a constant velocity. You guys are an inertial reference frame. You're at a constant velocity of 0. And then the two events are me snapping my fingers. So for example, when I'm next to student A and I snap my fingers, student A then records the time that I do. And then over here when I'm next to student B, I snap my fingers. Student B records the time when I do. Because those two events occurred in different locations according to this reference frame, what would then be recorded, the difference between the two times, would be an improper time interval. Now, in order to record this improper time interval, you need two clocks to do so. You would need two clocks, one with student A and one with student B, and those two clocks would be synchronized with respect to each other. And as I just described, student A would write down the time when I snap my fingers. Student B would write down the time when I snap my fingers. They compared the two, and then therefore they would record an improper time interval. Now you may be saying to yourself, well, wait a second, why don't they just use the wall clock in order to record this improper time interval? Don't they need just one clock? Well, consider the distance. Let's say the distance between the two students is not 10 feet, but is instead 10 light years. So then therefore, how would you record the improper time interval? You would have to do so exactly in the scenario that I just outlined. Now that's different from what is called a proper time interval. Okay, a proper time interval is a time interval between two events that occur in the same location. So consider the two events from my point of view. And let's say that I have a clock with me. Let's say that I'm wearing a wristwatch. And then therefore, event number 1 occurs like so. I note the time. Event number 2 occurs like so. I note the time. Therefore, the difference between the two is equal to the proper time interval. According to me, the two events, me snapping my fingers, occurred in the same location, right next to my head. Technically speaking, however, because the two events occurred in the same location, I only need one clock in order to record that proper time interval. Now, of course, in our everyday existence, if we actually performed this scenario, you guys, the stationary reference frame, would measure the improper time interval. Me, the moving reference frame, I would measure the proper time interval. And of course, the time intervals would be the same. They're not the same. Let's go ahead and understand why that is. In order to do so, what we're now going to do is take a trip through Einstein's imagination. Einstein always dreamt up these little scenarios, if you will, in his imagination to visualize the consequences of the postulates of special relativity. In the original German, these little scenarios are referred to as Gedanken Experiments. Gedanken is the German word for thought. When Einstein dreamt up these little scenarios, these Gedanken Experiments, he always used trains as a means of visualizing the effects of special relativity. The reason why is because in the early 20th century, the fastest mode of transportation was a train. So now let's take a trip through Einstein's imagination with this very famous Gedanken Experiment. And once again, the word Gedanken is German for thought. So we're taking a trip, if you will, through Einstein's imagination. And let's say that we have a train. Like so. And let's say that the train is moving in this direction relative to a stationary reference frame with a velocity u. And then let's consider the simplest type of clock. The simplest type of clock would be a ticking beam of light. The easiest way to illustrate this is to consider one of the arms from the Michelson-Morley experiment of the interferometer. So consider then the following. Let's say that right here is the source, and right here is the mirror. And then we're going to have event number one. Event number one will be the light leaving the source. And then when that occurs, here's student A. Student A is in the stationary reference frame O, and that person writes down the time, for example. Here's a little clock. That person writes down the time when the light leaves. And then according to the stationary reference frame, the light does the following. It leaves the source, and it strikes the mirror. So right over here, for example, is the source. Here's the mirror. And then the light reflects off the mirror back to the source. Like so. So right here is the source. Let me go ahead and draw the train. Like so. And right here is the mirror when the light returns to the source. This right here is event number 2. So event number 2 is that the light returns to the source. And then here's student B. Student B is in the same frame of reference as student A. That's the reference frame O. And student B right here has a little clock with him or her. That person then writes down the time when event number 2 occurs. Because the two events here occurred in different locations according to the stationary reference frame, you would then record an improper time interval. However, let's say that we have a moving observer. This is me, O prime. Like so, and I have a clock with me. And I write down the time when the light leaves the source. I write down the time, here I am once again, with my clock. When the light returns to the source, according to me, the two events occurred in the same location, therefore I would record a proper time interval. In our everyday existence, these two time intervals would be the same, but they're not the same. And here's why that is. Notice, by the way, that as I'm constructing this diagram, it looks familiar. It's one of the diagrams that I constructed when originally describing the Michelson-Morley experiment. But now the meaning is completely different. Notice I haven't said a word at all about the ether in quite a while. What can we now conclude about the ether? That it doesn't exist. We discard that idea completely. And then therefore, when I do construct this diagram, keep in mind now the new meaning. We have a stationary reference frame, you guys in this classroom. And then we have me on a train, the moving reference frame, and we're following a ticking beam of light. And now using this diagram, let's go ahead and calculate what we're going to refer to as delta T improper. In order to do so, like I did with the Michelson-Morley experiment, it's useful to take this diagram and divide it up into two, such that we end up with a right triangle. And now here are the various legs of the triangle. First of all, this distance right here. This distance right here is nothing more than the length L of the interferometer arm. Then we have this distance here. This distance here is the distance that the train moves in 1/2 of the improper time interval. This distance here is u times delta T improper, we'll now call it, divided by 2. And then we have the hypotenuse of the triangle. The hypotenuse of the triangle is the distance that the light moves in 1/2 of the improper time interval. How do I write that distance? Here's where the second postulate of special relativity comes in. Everybody sees the same speed of light, c. So then therefore, if student A and student B are here in the stationary reference frame O, they then see the speed of light as c. So this distance here then therefore is equal to the speed of light c multiplied by delta T improper divided by 2. And now we just use Pythagorean theorem to calculate delta T improper. Okay, so now this is all according to O. Using Pythagorean theorem, we now have L squared plus U squared delta T improper squared over 4 equals C squared delta T improper squared over 4, and now we just solve for delta T improper. So to do so, take this term here and subtract it to the other side. Like so. And then what I'm going to do is I'm going to factor out here from each term on the right-hand side a delta T improper squared over 4. That will then give us this. So take a look at that carefully. And now I'm going to go ahead and cross multiply the 4 here to the other side and then divide the parentheses to the other side to get delta T improper squared by itself. Like so. And now before I do the last step here, which is just to take the square root of both sides, what I'm going to do in the denominator on the right-hand side is one extra step, a step that you saw back in the Michelson-Morley experiment. What I'm going to do here is factor out a c squared from each term. Like so. And now I'll go ahead and just take the square root of both sides to get the improper time interval. So now over here on the right-hand board, delta T improper is equal to the following. So this expression here is the time interval that you guys would measure, the stationary reference frame, as the time interval between the two events. But now let's calculate what's referred to as delta T proper. This is the time interval between the same two events according to me, the moving observer. So now this will be according to O prime. So how do I find now delta T proper? Well, this is once again where the second postulate of special relativity comes in. Everybody sees the same speed of light. So then therefore on the top board, you guys see the speed of light as c. On the train, however, I also see the same speed of light as c. And speed equals distance divided by time. According to me, the distance traveled by the light on the diagram above is nothing more than 2L. Let's now go ahead and cross multiply to solve for delta T proper. So this right here is what I measure on my 1 clock. This right here is what you guys measure on your 2 clocks. Notice, of course, that the two are not the same. In fact, the two equations are combined together. When you combine the equations together, you end up with a very famous equation. Here's how I'm going to go ahead and combine those expressions together. Notice over here on the right-hand board that what is present is a 2L over C, which is delta T proper. So let's plug that in over there. Like so. And now as a last step, I'll go ahead and cross multiply the radical sign to the other side. Okay, when you do, you end up with a very famous equation. This equation is referred to as time dilation. Here's the expression. Like so. Now, which time interval is bigger, the improper time interval or the proper time interval? Well, this number here is a number that is less than 1. So then therefore, the proper time interval is less than the improper time interval. Delta T improper is greater than delta T proper. Less time elapses for me than it does for you. So here's literally what this equation is saying. According to you guys, I am moving. So then therefore, according to you guys, my clocks are running slow. Less time is elapsing for me than it is for you. In other words, I am aging at a rate that is less than you. However, according to me, it's you guys that are moving. So according to me, it's your clocks that are running slow. So then therefore, according to me, you guys are aging at a rate that is less than me. And both of us are correct. Now, if you're having trouble wrapping your head around this, don't worry, you're not alone. Here's the easiest way of thinking of it. Everybody sees the same speed of light, c, and speed is distance divided by time. However, according to the two reference frames in this description, the distances traveled by the light are different. Therefore, the times have to be different because everybody sees the same speed of light, c. So the entire scenario basically looks like this. The light beam goes out, hits the mirror, and then comes back. So you guys see the big triangle up there on the top board. Therefore, you measure a large amount of time, delta T improper. However, according to me, all that happens is that the light does this. It travels a lesser distance. So then therefore, because speed is equal to distance or divided by time, I will then record a lesser amount of time. So the proper time interval is less than the improper time interval. Okay, in part 3 of today's lectures, we'll go ahead and start to examine some examples.